Inside this labyrinth of pipes and chambers, super-heavy elements are being fused into existence. This machine is part of an international hunt to unlock the mysteries of this new class of elements that typically don't exist here on Earth.
Pushing these element discoveries really is pushing into models of how matter is formed in the Big Bang. How do we model matter, and how do we model the formation of the universe?
Super-heavy elements exist for a fraction of time and are nearly impossible to catch. But understanding them could force us to reimagine the most iconic scientific symbol of all time, the periodic table. In 1869, Russian chemist Dmitry Mendeleev laid the foundations for what would become the modern periodic table. He arranged the known elements in order of increasing atomic weight, starting with the lightest ones with the least protons and working his way up. And as he did so, a curious pattern started to emerge.
What happened is he noticed that at regular intervals, chemical properties were repeating themselves because of this periodicity in the chemistry. He realized that there were elements at that time that had not yet been discovered, but should be there.
In the following years, scientists started isolating the elements Mendeleev predicted from various materials. Scandium was found in a hunk of euxenite, gallium in a piece of zinc ore, and hafnium in a zirconium mineral, to name a few. The table's design was revised and perfected as more elements were added. But as nuclei got heavier and heavier, finding them became a bit more complicated.
When we refer to heavy elements, we're talking about things that have these very large nuclei that have a lot of protons in them.
Above uranium, nothing exists here naturally. They have more protons in their system than anything that we have naturally occurring.
In order to continue their quest towards a complete periodic table, scientists couldn't just continue isolating elements from existing materials. They had to create them.
So we use what's called a particle accelerator, or specifically a cyclotron, which is a large instrument that accelerates ions to a fraction of the speed of light.
Cyclotrons have been used to discover heavy elements ranging from curium to plutonium. And most recently, Dr. Shaughnessy's team collaborated with a lab in Russia to complete the periodic table's 7th row, the home of the superheavies.
When we make one of these new elements in the cyclotron, we really have to just add up protons. So for instance, if we wanted to look for element 116, we could take something with 20 protons, and we can take something with 96 protons. And if we can get those two nuclei to completely fuse together for even a short time, that means we have an element 116, one atom of it. These elements are very short-lived. They're not very stable, so they decay very quickly.
Some superheavy elements only exist for just milliseconds. So in order to confirm they created one, the team had to work backwards, sifting through the data to find the signal that told them a heavy element was actually there.
The Flare-Off lab in Dubna has an incredible cyclotron that's really a workhorse. And we at Livermore have access to various target materials. So we provided our expertise, the Russians provided their expertise, and together discovered elements 114 through 118.
While efforts to discover more elements continue, Dr. Shaughnessy and Dr. Gates have shifted their sights to studying the ones we already have. We know almost nothing about these super heavies, including whether or not we've actually put them in the right place on the periodic table.
Right now, when an element is discovered, we're putting it in the periodic table based on its number, mostly for convenience. But the periodic table, let's remember, was constructed to be a living document on the chemistry of these elements.
So the models predict that these heavy elements might behave unexpectedly due to something called relativistic effects.
We have these big, massive nuclei, and what's happening is they're accelerating their electrons to near relativistic speeds. They're going so fast that they're being dominated by the theory of relativity. And what that does is it's changing the mass of the electron, and that's changing how it bonds and its chemistry. So when we get to this last row of the periodic table, what we see sometimes is that the chemical properties down a given group may invert or do something totally different.
We believe that we have them in the right position, but we also don't think we've proven that. And so what we did was we built Fiona to actually prove that what we think is true actually is true.
Hooked up to the Lawrence Berkeley National Lab's 88-inch cyclotron, Fiona is one of the newest tools designed to study superheavy elements. Its primary goal is to experimentally confirm their mass numbers. But before Fiona can measure the mass, the team needs to create a superheavy element.
So we are in Cave 1 at the Building 88 facility. The beam comes from the cyclotron, which is right through that wall. And then it travels all the way down this line here until it reaches our target on the other side. This is what our targets look like, or this is 3/4 of a target. We have just a couple thousand atoms thick of whatever our target material actually is. What we're interested in is one nucleus from the beam hitting one nucleus from the target and completely fusing. The problem is that doesn't happen very often. Nuclei are very small compared to atoms. So a nucleus is about 10,000 times smaller than the atom itself. So when the beam comes in, what it actually sees is mostly empty space. So it actually passes through our target, mostly. And then very, very rarely, we'll get this head-on collision that makes that atom that we want. Right inside this box, that's where our elements are made. Now our job is to find a way to separate all that junk that we don't want from that one atom that we do.
Everything travels through the Berkeley gas-filled separator, a machine equipped with giant magnets that bend the excess atoms away from the superheavy the team is interested in. Then it enters stage 1 of Fiona.
That's all of that equipment over there. It traps it in a small volume, and then it sends it on to stage 2 of Fiona.
Magnetic fields then send the superheavy atom into a specialized loop. And it's the specific path it takes within that loop that tells the team its mass.
Fiona's first scientific experiment started in June of last year. We were able to confirm that those new heavy elements that we've discovered really do have the number of neutrons and protons that we think that they do.
But confirming that isn't quite enough to know for sure that we've put them in the correct place on the table. We also have to explore their chemistries.
We have atoms trapped in a cubic millimeter of volume. For a time that we pick, we can add in different gases, and we can change the amount of time we trap things for. We can look, does this gas react with this atom? And if so, what does it make? We can actually learn quite a bit about the chemistry of these new elements.
And at Dr. Shaughnessy's lab, her team is looking into alternative methods.
Here at Livermore, we're trying to develop a way to do aqueous chemistry of 114. So hopefully this collection of data from both the gas and aqueous phase will start to paint a more complete picture. If we do see some real shift in chemistry, we would have to rethink that last row. What does that mean for our periodic table?
150 years after its conception, the periodic table is reaching a turning point. As Dr. Gates, Dr. Shaughnessy, and teams around the world continue to unlock the mysteries at its borders, they're also starting to question just how much further those borders can be pushed.
There are people who have tried to predict where the periodic table will end. The most common number thrown about is around element 172 or 173.
The issue is that the probability of making the two nuclei come together, it gets smaller and smaller as we go up in element numbers. So with element 118, it was a very small probability that we would make it. Now for 119 and 120, it's even getting lower and lower. In order to push out to heavier elements, there's going to have to be some real shifts in technology compared to what we have now.
You're trying to answer a basic scientific question. How many elements are there in the universe, and what are their chemical properties? And that's something that's interesting regardless of whether or not there's any scientific applications for it.
If you break down an advanced piece of technology, a new medicine, or an energy source to its essential parts, you always end up with the same thing. Those same blocks that make up you and me and the stars in the night sky. It's about the elements themselves.
The formation of these elements alone tells us a lot about nuclear theory and how the nucleus holds together. We've already changed over the decades how we think of the nucleus. So that's where the application is right now, is really in just our fundamental understanding of the universe.